Welcome back. Let's take a look at another example. Might we be able to predict life expectancies from birth rates? So it says, provided is the bivariate data giving birth rate and life expectancy information for each of 12 countries. For each country, both X, the number of births per 1,000 people in the population, and Y, the female life expectancy in years for that country, are given. Also shown are the scatter plot and the least squares regression line. All right, so let's begin here with part one, and we're going to test for the significance of the correlation coefficient. So first step is enter the data into L1 and L2. I've done that. If you'd like to pause and enter in the data, we pick up from there and write our hypotheses. All right, so we have our null hypothesis and our alternative hypothesis. So our null hypothesis will always be that the population correlation coefficient, rho, so there's our population correlation coefficient equals 0. So that would mean for the population of all countries, not just the 12 in this study, but for the entire population of all countries, that there is no linear relationship between these variables. And then we go out and get some data to see if we find evidence that rho is significantly different from 0, indicating that there we do have evidence to support a claim of a linear relationship. All right, let me spell relationship correctly. Relationship. All right, so in order to test the claim, we run a linear regression t-test and find the sample correlation coefficient. All right, so we'll go to stat tests, and instead of scrolling down, I scroll up because it's towards the bottom of the list. Linear regression t-test, my data XL1, YL2, frequency always 1, rho not equal to 0 is always our alternative. Regression equation, you can leave that blank, and then I'll hit calculate. And I'm going to scroll to the bottom of that screen and we'll find our sample correlation coefficient. I'm going to round that to 3 decimal places, so that's 0.916. So that does appear to be getting close to a -1. So we want to figure out if that is a significant bit of evidence by evaluating the p-value of the test. So let me scroll back up. And you'll see my p-value here is very small. In fact, the calculator switched into scientific notation, the E-5. So just so we can round here, what I'm going to do is just take the very first digit 2 and round it. It has an 8 next to it, so that 2 would round up to 3. So in the notes here, I'm just going to write 3, and then I'll deal with the E-5. So we'll move the decimal left 5 places. So it will be 0, 0, 0, 0, and then 3. All right, very small p-value. We're going to compare that to a significance level alpha of 0.05. So there's my p-value, and there's my alpha. And this p-value is certainly smaller than that alpha. We usually say technically less than or equal to, but it is indeed smaller. All right, and then our rhyme is, when the p-value is low, let the null go. So our p-value is low, so we will be rejecting the null hypothesis, which means that our correlation coefficient for our sample is a significant value. And when we reject the null, we always support our claim. So there is evidence of a linear relationship between birth rate and female life expectancy. All right, so that's called correlation. And then if we conclude that there is a linear relationship between the variables, we move on to regression. So regression is where we come up with the equation of that line that describes the relationship. So the calculator took care of that for us. So just as a reminder, with the regression equation, we do not use the letter y. We do y hat or y prime. The idea is just it has to be a different symbol because y represents actual data values in the study. This is going to be the equation of that line that best fits that trend that we're seeing. And then the calculator writes it in the form a plus bx. So our value for a, rounding to one place, is 81.4. And then plus b, but b is negative. So instead of writing plus a negative, we can just write subtract. And rounding that to one decimal place would be 0.4. So 0.4. And then we write our variable x. All right, so that's our regression equation. All right, next part says pairing. So when we're talking about pairing, we're looking for the relationship between these two variables in terms of, I'm going to point here, the slope of that line. So the slope is the b, the coefficient of the x. So we've got an equation here with a negative slope, which means as one variable goes up, the other variable goes down. So that's what they're referring to with pairing. So for these data, female life expectancies that are less than the mean of female life expectancies, they tend to be paired with, so because it's a negative slope, I call this opposite pairing. If those are less than the mean, they tend to be paired with the opposite here, which would be birth rates that are greater than the mean. So I just like to think of it as opposite pairing when I have a negative slope. All right, and then C. According to our regression equation, for an increase of 1 birth per 1,000 people in birth rate, there's a corresponding decrease of how many years in female life expectancy. So when we see that phrase, for an increase of 1, they're referring to interpreting the slope of the line. So the slope of the line is, again, the coefficient of the x, the value for b. And in order to interpret it, I'm going to write it over 1. So negative 0.4 over 1. So we can just remember here, slope is the change in y over the change in x. So when they're writing that statement, that increase of 1 is referring to the denominator. So x represented birth rate. So for an increase of 1 in birth rate, I would expect, so it already says decrease because it is a negative, so a negative slope. So I would expect a decrease of how many years, and that would be 0.4. So they said the word decrease, so we want to say 0.4 years. Okay, and then for D, from the regression equation up here, what is the predicted female life expectancy in years when the birth rate is 45.4 births per 1,000 people, right? So the idea is I can now use this equation to make predictions about any country that has this particular birth rate. So they're giving us a value for X, so a country with a birth rate of 45.4. And we know to predict, we can substitute into our regression equation. So now I'm going to just substitute. So 81.4 minus 0.4 times 45.4 substituted for X. All right. So we have 81.4 minus 0.4 times 45.4. And we'll stick with one decimal place, so 63.2. And then it says, what was the observed female life expectancy when the birth rate was 45.4 births per 1,000 people? All right, so predict means use your regression line. So that value for y hat is what we predict. When it says what was observed, that's going to be the value of y that we actually saw in our study. So there was a country that had a birth rate of 45.4. So we have to go back up to that table. So if we look at our 12 countries in our study, there's the country that had a birth rate of 45.4. And in that country, female life expectancy was 58.1 years. So let me write that at the bottom, and I'm going to come back to the graph here. So that's 58.1 years versus we predicted 63.2 years. All right, so the way this works is the predicted value represents, on average, all the countries with a 45.4 birth rate. This is an average of the female life expectancy. So not every country would be exactly that value. In fact, this country is below that average. So up on the picture, I'm just going to end here with labeling these values. So 63.2 is what we predict. 58.1 is what we observed. So on my picture here, the 45.4 would be basically that point. So let me just label that one. So that's the XY value that was observed for this particular country. And then the equation of the regression line, so that line was used to predict the female life expectancy. So for that same value of X right above it, that point on the line is the predicted value. So it's above. So it's above the life expectancy for this country. So this country is a little bit below what I would expect on average. And then just to complete it here, so 45.4, and we predicted a life expectancy of 63.2 years. Okay, so that problem is a good summary of the whole process of correlation and then regression.